Okay, so up next is Aurélie Edelin. She's finishing her PhD at Colorado State University and Fermilab, where she's been working on applying neural networks to modeling and control problems in variparticle accelerator systems. We're excited to have her here, so welcome, Aurélie. This microphone for the recording. You can point if you want to with this, but there. Okay. I'll tell you when you okay.
Thanks. I'm happy to be here. I should preface this by saying that the work I'm about to present is something that I kind of picked up on the side for fun, so I would say it's pretty preliminary. The motivation here is that in FEL light sources, there are typically a lot of different kinds of scientific users who have very different needs as far as the photon properties go. So typically, you'll have these facilities switching fairly frequently between different sets of machine settings to support those various users. And the way that this is typically done now is you'll have some sort of saved group of settings that hopefully get you close to what the specific user has requested. However, those are typically fairly sparse. It's just giving you a discrete set of settings, and typically there will be quite a bit of drift in the machine over time. So you might not be very close, even if you are restoring all of that. And typically, you'll have human operators tuning the machine to get it closer. We're just starting to use online optimization a little bit, but for the most part, there's a lot of hand tuning. So that overall ends up reducing the scientific output of the facility for a given operational budget, and overall adds to the cost quite a bit. So it would be really nice to have some sort of tool that can give suggested settings for a particular photon beam request. And it'd be nice if this could be valid over the whole parameter space, and also if you could update it over time as you visit new states. So doing this for something like LCLS right now is probably out of the question, just because it's so large in scale. So we decided to start with a smaller test case. This is a pretty small FEL. It's one that was previously operational in the Netherlands, and there were plans to rebuild it in the US. That's been stalled, but maybe someday it will be built. And one of the reasons why this is interesting is because you've got a fairly small number of components that you need to adjust, but this system actually has kind of a lot of nonlinear beam dynamics in it. So it's a nice little test case. So if you want a particular wavelength of light out of the undulator, what do you need to do? Well, you need to get certain electron beam properties right at the entrance of the undulator. And in the simplest case, that's just related to the beam energy and the strength of the magnets in the undulator. In reality, it's a little bit more complicated. But ultimately, what you mostly care about is that the beam size and the beam divergence is such that you can transport through the undulator, and you want to minimize this parameter called the emittance of the beam, which is just the total area of the beam in position, momentum, phase space. And alpha and beta have specific definitions within that framework too, but roughly they're the beam size and divergence. The way that you achieve those parameters right in front of the undulator is by adjusting quadrupole electromagnets. So these are focusing in one plane and defocusing in the other. And if you have a beam that does not have strong self fields, so it's not interacting, the individual electrons in the beam are not interacting that much with each other, then in principle that only affects the beam size and divergence. But in this system, and in any system where those self fields are significant, it also affects the emittance significantly. And then upstream, where you actually are producing the electron beam, you have a couple of different knobs that you can tune. So the RF power in this cavity will determine the energy of the electrons. You also generally have to set the RF phase and set this solenoid and bucking coil so that you are getting optimal emittance out of the injector. So the end goal here is to specify what the RF phase, RF power, the solenoid strength, and those 5 quadrupole settings should be to get specific emittances, beta function values, alpha function values, and energies at the entrance of the undulator. So for this system, we do have a physics-based simulation. This is just a standard particle tracking code out of Los Alamos, and it includes the beam self-fields. Those are pretty computationally expensive. And then the way that this works is you just load the electromagnetic field maps for the cavity and then for the solenoid and bucking coil. Unfortunately, because this is a code that was produced by Los Alamos, it's distribution restricted, and we don't have the source code, and it's compiled for Windows, so we couldn't just run it on a cluster and train a controller by interacting with it a lot. So we decided to learn a neural network model from a set of simulation results. And this has some nice perks. So, I mean, first of all, it's faster executing than the physics-based simulation, but also we can then update it with measured data. So train first in simulation, and then whatever measured data we have, we can now just update that model. And also, it's nice to have a differentiable model. More broadly, if you were trying to do something with a real machine, machine time, and by machine, I just mean an accelerator, it's terminology in the field. It's really expensive typically, so any time that you would be trying to train a controller, you're not going to have a lot of beam time to do it, so you're probably going to be looking at archived data and building up a model anyway. So in both cases, when we're trying to use the simulation and if we're trying to interact with the real machine to learn something, sample efficiency of the learning algorithm matters a lot. And then also, by learning this model, it's useful for any kind of control development, and it's actually useful for other operational tasks and accelerators. So doing something like diagnostics, for example. So in this case, this is just sort of the inverse of what we showed before in the model case, except that now we're also predicting the number of particles. Transmission is really important for estimating any of the other beam parameters. So we want to predict that as well. So there are a number of ways that we could have set up our training data set. We could have just done broad parameter scans, but one thing that we were thinking about is if we wanted to go and then take this to a real machine, what would we be using to train on? And a lot of times for larger accelerator facilities, you don't have a good physics-based model just because you're dealing with lots of systems that are put together and there are lots of compounding errors. So if you're using measured data, what's actually already in the archive of a real facility? And usually what you'll see is lots of noisy data and then lots of tuning around roughly optimal settings. So what we decided to do was come up with a training set that kind of mimicked that a little bit. So we interfaced with the physics simulation with an optimizer to optimize all of the beamline settings for specific target energies. And then trained a forward model using all of those samples, and then left one energy range out for validation. And we wanted to then actually make use of that data for initializing the control policy. And unfortunately, the model is not invertible, so just using all of the data won't work. But we can at least use the converged settings to just get it started. So we trained the inverse model on the converged samples, and then that ends up being the initial policy. So here, all we really care about is just roughly getting to the correct settings. And then after that, you can either do finer tuning with some of the efficient local tuning algorithms that we already use in accelerators, or retrain the model and the control policy. So to start with, we just have a batch of target beam parameters, put that into the policy, get a predicted set of settings, send that to the forward model, the weights of which are frozen in this case, get the predicted set of beam parameters, and then that goes into the cost function. In this case, it's both the difference between the requested and the predicted beam parameters, and also a penalty for transmission. As soon as you are losing beam, you can no longer really estimate the other parameters as well. And on top of that, in general, that's the first thing that we care about is, are you actually getting the beam through the accelerator completely? And we also penalized higher magnet settings, the idea being that if you can find a solution that works sufficiently well with sending the least amount of current to the magnets, that's reducing your operating cost a little bit. And then for every nth iteration, because here we were dealing with a simulation, so it's expensive to get, you could update it at each iteration, but in this case, we just took a batch every once in a while of the predicted beam parameters and the settings that were coming out of the policy, and then used that to update the model every once in a while. And then we tested the policy directly on the simulation. So the details of how we did this for an initial study was we used Nelder-Mead and LBFGS for getting that initial training set, and we used 12 different beam energies between 3.1 and 6.2 MeV, which is the full operating range for that accelerator. And so this is just an example of what the training data set looks like. So these are just all of the quad settings for about half the training data set. So then the model was just a simple feed-forward network with 4 hidden layers, 8 inputs, 8 outputs, and we, again, held out one set of the optimized energy ranges for the validation. And then there's a little nuance here, which is that because all of the beam parameters are being estimated based on just this cloud of particles that we have, those estimates are only valid when you have good transmission. So we only update those outputs when the transmission is above 90%. And so to start with, we wanted to focus on just getting alpha and beta correct for a given energy. So here we didn't allow much variation in the gun settings. Gun is just another name for the injector beyond the known optima that we already have. And then we excluded the emittance and the cost function. And this was the structure of the policy network. And again, we excluded a specific energy range for the validation set and gave it target desired energies. And in this case, we left alpha and beta the same. So one could imagine saying maybe I want my divergence to be not 0 in some case, but here we just left it constant. So how did this do? Well, it did okay. This is just an example of the model performance on the validation set. So this is this is beta X, and the model performance was pretty good. When training the controller, we really only cared in this case about how close it could get in one iteration, and that seemed encouraging. It was generally within about 10% of where we wanted it to be, and the beam was pretty close to a waist. So what that means is essentially you wouldn't need to do much further tuning, assuming that there wasn't any drift in the machine. So with that in hand, we are currently working on extending this. So now we're including minimization of the emittance, and then also allowing the policy to actually adjust the injector settings a bit more. So this also requires a lot of finer start-to-end adjustments for the machine. So we needed to get some more simulation data to actually learn an accurate model and also increase the size of it a bit. So it's quite different. And another critical thing is assessing how well this actually performs when we do have drift in machine behavior. So this can be things like there's a deviation between the settings that you're issuing and what the real values end up being, or maybe the responses from the beam are a little bit different for some reason. So that's a critical element of that. We also need to directly compare it with other methods. So for example, it might actually be more efficient just to use model-free RL. Probably the first thing to try is trust region policy optimization, just to compare. And then also, because right now the sort of state of the art for accelerators in doing tuning is just doing online optimization. We need to directly compare with that. And after that, the next step would be just trying to get this approach running on an actual machine. So we have a few plans for starting to do that. First, just looking at the data that is available for a couple of different facilities, and then moving on from there. There's some other tweaks that we're looking at making. So the weights of the cost function in particular should probably be tuned a little bit more rigorously than they have been so far. And right now, I'm also just specifying directly what the raw value of the setting should be rather than a change in the setting. So we may do that instead and then not do the pre-training with the inverse model. Remains to be seen which approach is more advantageous. So in conclusion, this was just an initial study trying to see whether this would work for a small system, and that looked encouraging. So we're continuing that with a more complete study, and it'll be interesting to see whether this sort of thing can actually be scaled up to a real accelerator facility. That'll be quite a task. There's a lot of things that change in an accelerator facility all the time. So equipment breaks and gets replaced, and calibrations change. They're challenging systems to work with. So maybe down the line, this sort of approach could be implemented. And that's it. Sorry.
Thank you one more time. We have time for a couple of questions. Does anybody have any questions? Oh yeah, sorry. Go.
Have you tried somehow collecting data from just what operators have done historically and somehow followed a path like that?
Yeah, so not for this work. Actually, for a separate set of work that I've been doing with resonant frequency control and normal conducting cavities, this is actually at Fermilab. There are some operators that were sort of manually doing the RF ramp over time during startup. And they were doing this repeatedly day after day. So I did look at trying to learn that policy that they had come up with effectively. And I don't think that they were consistent enough from day to day in the way that they were doing it to actually really learn it adequately. I didn't dig into it too much, and ultimately just using model predictive control with a learned model ended up being better anyway. So, but I think that's a really interesting approach, especially if you do have sort of routine tasks where you might be able to actually extract what the operator was doing heuristically.
As a follow-up, is that data routinely collected, or you would have to go and change things so that it could be collected more efficiently?
It really depends. Some accelerator facilities are very good about having complete data archives, so you can go in and pull out pretty much the values for any parameter over time that you wanted, as long as someone had previously put in that parameter should be logged at some rate. Other accelerator facilities do not do this at all, and it's very hard to access any historical data, and you would have to decide ahead of time that I want to look at this specific set of data, and now I'm going to collect it in the background for some amount of time. So it's really variable.
One last question.
Have you thought about hybrid human AI systems for tuning?
So in what context?
I guess like in the context of like maybe there are some parameters of this I guess so the cases where say like maybe like a physicist would like look at the input from a system like yours.
Yeah, so I mean,
Like
Yeah, I imagine there are a lot of different ways that you could do that. And actually right now, sometimes you'll get operators running an optimizer just separately on a physics model that they have. And then they'll look at what the suggested settings were, and then just manually enter them into the accelerator. So, I mean, yes, you can imagine the same sort of thing for an AI system. I'd imagine there could also be some more sophisticated ways of having a human in the loop. But yeah, it's something to think about.
Okay, let's thank our speaker one more time. All right, we have a break now for a poster session. If you are one of the authors, we'll be distributing the tape that you'll need to hang up your posters in the back corner over there. You can use any of the walls, but please do use the correct tape. The talks will resume at 11 with Gilles Loup's talk, so stay tuned for that as well. Thank you.